385 million years ago, trees didn't just grow tall, they grew impossibly tall. We're talking structures that reached 40 miles into the sky. 40 miles, that's higher than commercial airplanes fly today, higher than where the atmosphere starts thinning into the void of space. And at the top of these biological skyscrapers, in an atmosphere nothing like what we breathe now, something was living. This isn't speculation. This isn't fringe theory whispered in paleontology backrooms. The fossil record proves these giants existed. Prototaxites, lepidodendron, sigillaria, names that belong to organisms so bizarre that for over a century, scientists couldn't even agree on whether they were plants, fungi, or something evolution invented once and never tried again. What the fossil record doesn't tell us, what it can't tell us, is what thrived 40 miles up in that alien canopy ecosystem. But physics can tell us, biology can tell us. And the implications are so deeply unsettling that most textbooks skip right past them. Because if these trees existed, and the evidence says they absolutely did, then everything we think we know about the limits of terrestrial life is fundamentally wrong. The vertical dimension of Devonian ecosystems wasn't just tall forests. It was a biological frontier that makes the Cambrian explosion look quaint. And then it vanished. Completely. Catastrophically. Leaving almost nothing behind except fossilized stumps and the physics equations that prove the impossible actually happened. Let me paint the picture. The Devonian period. 385 million years ago, Earth was unrecognizable. The continents were still clustered in strange configurations that would look alien on any modern map. Pangaea hadn't formed yet. The supercontinent Gondwana dominated the southern hemisphere, while smaller landmasses drifted in tropical seas. And across these landmasses, the first forests were doing something no ecosystem had ever done before. They were building upward. But these weren't forests like anything alive today. There were no birds because birds wouldn't exist for another 150 million years. No mammals, no flowers, no grass. The most advanced land animals were arthropods, oversized ancestors of scorpions and millipedes, some stretching 10 feet long and armored like tanks. The apex predators were meter-long sea scorpions patrolling shallow coastlines, and towering over all of it, dominating every horizon, were the giants. Prototaxites looked like massive tree trunks but weren't trees at all. They were fungi, or maybe lichens, or maybe some chimeric organism that blurred every category we use to classify life. They grew in spiraling columns, some reaching over 20 feet in diameter and hundreds of feet tall. But the real giants, the biological impossibilities that broke every rule, were the scale trees and club mosses, lepidodendron, sigillaria. These names sound technical and boring until you understand what they represent. Scale trees that grew at speeds that would make bamboo look sluggish, hollow-trunked giants with bark patterns that looked like reptile scales, hence the name. And they didn't have roots like modern trees. They had shallow rhizome systems, sprawling networks that spread horizontally instead of digging deep. Because they didn't need to dig deep, the water they needed wasn't just in the ground, it was in the air. The Devonian atmosphere wasn't our atmosphere. Oxygen concentrations hovered around 35%. Today we breathe 21%. That 14% difference wasn't just richer air, it was denser air, heavier air, air with different pressure gradients from sea level to stratosphere. And in that heavy, oxygen-rich atmosphere, the physics of biological pumping changed completely. Modern trees hit a hard ceiling around 300 feet, because capillary action, the mechanism that pulls water from roots to leaves, simply can't overcome gravity beyond that height. The tallest living redwoods max out just under 400 feet, and they're struggling at that altitude. Their upper branches are stressed, stunted, desperate for water that takes weeks to climb from the root system. Physics says this is the limit. Biology agrees, but the Devonian giants said otherwise. 40 miles, 211,000 feet, 500 times taller than the tallest redwood alive today. At that height, you're not in the troposphere anymore, you're not even in the lower stratosphere. You're pushing into altitude ranges where modern plants can't survive, where the air pressure is 1% of sea level, where temperatures plummet to -60 degrees Fahrenheit, and UV radiation bombards every surface, with enough energy to shred DNA. So how did they do it? The answer starts with the 35% oxygen atmosphere. Higher oxygen doesn't just mean richer air, it means the entire pressure curve from ground to sky shifts. The breathable zone extends higher, the density gradient changes, and for organisms that evolved in that environment, mechanisms that seem impossible in our world become routine. Some paleobotanists theorize these trees didn't rely on capillary action at all. They used atmospheric pressure differentials. Imagine a hollow tube hundreds of feet tall with selective membranes at different heights. Pressure differences between the dense air at ground level and the thinner air above create a pumping effect. Add in symbiotic microorganisms living in the vascular system, bacteria or archaea, that actively move fluids as part of their metabolic processes, and you get a biological pump that doesn't fight gravity. It uses atmospheric physics. But even if we solve the water transport problem, we're left with a bigger question. What lived up there? At 20 miles, 30 miles, 40 miles into a Devonian sky? Because wherever there's an energy source, wherever there's a niche, life finds a way to exploit it. And the canopy of a 40-mile tall tree wasn't empty space. It was real estate. Valuable real estate bathed in unfiltered sunlight with access to atmospheric resources nothing on the ground could reach. Start with the foundation of any ecosystem. The primary producers, photosynthetic organisms. The tree itself was covered in structures designed to capture light, probably from top to bottom, but the canopy was the prize. Maximum sun exposure. No competition from neighbouring trees because at 40 miles up there were no neighbours. Just open sky and radiation pouring down from a sun that looked different from that altitude, harsher and whiter without the atmospheric filtering we take for granted. The tree's photosynthetic structures, whatever they were, would have been working at maximum efficiency. But they wouldn't have been alone. Symbiotic organisms would have colonized every surface. Algae, protolichens, biofilms of photosynthetic bacteria forming thick mats on the bark. Living solar panels soaking up energy and converting it into biomass. And wherever there's biomass, there's something trying to eat it. Enter the arthropods. The Devonian was the age of arthropods on land, and these creatures had already proven they could grow to monstrous sizes in the oxygen-rich air. Dragonflies with 2-foot wingspans, millipedes as long as alligators, sea scorpions in the oceans reaching over 8 feet. But size wasn't the only innovation. Specialization was. And if you're an arthropod in a world where the biggest, richest food source is a living tower stretching into the clouds, evolution pushes you upward, fast. Fossil evidence shows that many Devonian arthropods had appendages specifically adapted for vertical movement. Clawed segments, adhesive pads secreting sticky compounds, hooked limbs designed to pierce bark and lock into place. These weren't adaptations for crawling on flat ground. These were climbing tools, specialized equipment for an ecosystem where up and down mattered more than forward and back. Now imagine the canopy ecosystem at 20 miles altitude. The air is still thick enough to breathe if you're adapted for high oxygen, but it's noticeably thinner than ground level. The temperature is cooler, the UV radiation is intense, and the tree's surface is covered in photosynthetic organisms pumping out calories. This is where the herbivores lived, not the massive ground dwellers. Those couldn't make the climb. Specialized canopy arthropods, lightweight exoskeletons to reduce the energy cost of climbing. Powerful gripping appendages, possibly even primitive wing structures, proto-membranes that allowed gliding between trees or riding thermal updrafts. These weren't aimless grazers. They were adapted for three-dimensional movement in a vertical world. Some probably lived their entire lives in the canopy, hatching from eggs deposited in bark crevices, feeding on biofilm, molting and growing in the open air, never touching the ground until they died and fell. And that's if they fell at all. Because at 40 miles up, when you die, you don't necessarily drop straight down. Wind currents at that altitude could carry a lightweight arthropod carcass hundreds of miles before it ever reached the forest floor. Which means most canopy life never fossilized. It just scattered. But herbivores don't exist in isolation. Wherever there's prey, predators follow. carnivorous arthropods hunting the canopy feeders, ambush predators clinging motionless to bark, compound eyes scanning for movement, waiting for some unwary herbivore to wander into striking range. Pursuit predators that could chase across vertical surfaces or leap between branches if these trees even had branches. The fossil record shows that Devonian scorpions had venom sophisticated enough to paralyze large prey instantly. Now scale that to a canopy ecosystem where falling means a 40-mile drop into oblivion, and you understand the evolutionary pressure. These predators didn't just sting to kill, they stung to lock prey in place. Neurotoxins that froze muscle systems while keeping the victim alive. Because at that altitude, a dead arthropod loses its grip and falls. A paralyzed one stays put, locked to the bark by its own frozen limbs. Fresh meat on a vertical surface. The predator could feed at leisure, inject digestive enzymes, and consume liquefied tissues without worrying about the meal disappearing over the edge. But the ecosystem didn't stop at 20 miles. Remember, 40 miles. If life adapted to 20, what stopped it from pushing higher? The answer is nothing stopped it. The atmospheric gradient was a ladder. Each altitude zone had different conditions, different temperatures, different pressures, different levels of radiation, and each zone selected for different adaptations. Low canopy zone, 10 to 15 miles up, air still thick enough for larger organisms, UV exposure manageable with the right biochemical defenses, probably melanin analogues or reflective exoskeleton structures. This was the Serengeti of the Devonian sky. The bulk of canopy biomass lived here, herbivores grazing on photosynthetic mats, predators hunting the herbivores, scavengers waiting for something to die and trying to claim the carcass before it fell. Mid-canopy zone, 20 to 30 miles, air thinning noticeably, temperatures dropping toward freezing. Only specialized organisms survive here. Smaller bodies to reduce oxygen demands, faster metabolic rates to generate heat. Adaptations we don't see in modern species because the atmospheric conditions that selected for them no longer exist. Exothermic chemical reactions in specialized tissues. Antifreeze proteins in their hemolymph, the arthropod equivalent of blood. Reflective or insulating setae covering their exoskeletons to manage the thermal extremes. This zone was the deep ocean equivalent of the canopy, sparse populations, wide territories. Organisms that were functionally alien compared to anything living on the forest floor. They didn't just survive in harsh conditions, they required harsh conditions. Their biochemistry was tuned to low pressure and high radiation. Bring them down to ground level and they'd probably suffocate on the rich, dense air. Upper canopy zone, 35 to 40 miles, the edge of the possible. Even in a high oxygen Devonian atmosphere, this altitude pushed biological limits. The air here was a thin whisper. The temperature was brutally cold. Radiation levels were high enough to damage unprotected tissues within hours. And yet, if the tree grew there, something lived there. Extremophiles, organisms that shouldn't exist by our standards, but did because evolution doesn't care about should. Tiny arthropods, possibly microscopic by that altitude, clinging to the topmost structures with adhesive pads that could grip in near vacuum conditions. Feeding on wind-borne organic particles, dead skin cells and spores blown up from lower altitudes, living in a freezing, irradiated environment that we would classify as uninhabitable. Why would anything adapt to live there? Because at the very top there was no competition. Zero. The herbivores couldn't climb that high. The predators had no reason to follow. It was the loneliest niche on the planet. But it was stable, predictable. And for organisms that could tolerate the extremes, it was paradise. Endless sunlight, no threats, just the slow, patient work of filter feeding atmospheric debris in the silence of the stratosphere. Now here's where this connects to revisionist economic history. These trees didn't just support ecosystems, they created economies. Biological economies where energy, the universal currency of life, flowed vertically instead of horizontally. The ground level was resource poor, shaded by the canopy, lower oxygen concentrations due to decomposition and soil respiration, competitive pressure from massive ground-dwelling arthropods. If you wanted to survive as a small organism, you climbed. You had to. The higher you went, the more resources you accessed. More light, cleaner air, less competition, But the higher you went, the harsher the conditions. It was a vertical gradient of risk versus reward. And the organisms that won that game, that claimed the highest niches, were the most specialized things the Devonian produced. They were biological extremists optimized for conditions that existed nowhere else on Earth. And when those conditions disappeared, they died. All of them. Because around 360 million years ago, everything changed. The oxygen levels began dropping, slowly at first, then accelerating, from 35% down to 30%, then 25%. The atmospheric pressure shifted, the density gradient flattened, and suddenly the physics that had allowed 40-mile tall trees stopped working. Imagine the collapse. A tree that size doesn't just fall over. It doesn't tip like a redwood in a storm. It fails structurally. Internal stresses that were balanced for 300 years suddenly exceed material tolerances. The trunk buckles, snaps, and 211,000 feet of plant matter comes down in a cascading failure that registers as an earthquake. The shockwave from a falling giant would flatten everything in a 5-mile radius. The debris cloud would block out the sun for weeks, splinters the size of telephone poles embedding themselves in the ground like javelins. And the organisms living in the canopy? They didn't evacuate. They couldn't. They fell with the tree. 40 miles, 211,000 feet. Terminal velocity for an arthropod in Devonian atmosphere was probably lower than modern air, but it didn't matter. The impact was still fatal, and their bodies, light and fragile, would have shattered on impact or been buried in the debris or scattered by scavengers before fossilization could even begin. But the physical destruction was just the beginning. The real catastrophe was ecological. Every organism that had spent millions of years adapting to the canopy, that had specialized for high-altitude survival, suddenly had nowhere to go. The vertical economy collapsed, the energy gradient disappeared, the niches vanished, and the specialists, the extremophiles that had claimed the highest zones, went extinct. Not slowly, not with some struggling remnant population clinging to survival. They just stopped existing. We don't have fossils of those organisms. We probably never will. Fossilization requires specific conditions: rapid burial in fine sediment, anoxic environments that prevent decomposition, protection from scavengers. The canopy organisms lived in the worst possible environment for any of that: high, dry, exposed to wind and scavengers. When they died, they decomposed in place or got scattered across hundreds of miles. The fossil record is biased toward things that die in swamps, in river deltas, in environments where burial happens fast. It's blind to things that die in the open air, but absence of evidence isn't evidence of absence. It's evidence of bias, a systematic bias in our data that makes us think ground-level ecosystems were all that mattered. That vertical stratification was just a minor detail. But what if it wasn't? What if the canopy ecosystems of the Devonian were more diverse, more biomass-rich, more evolutionarily significant than anything happening on the forest floor? We'd never know, because they didn't fossilize. Let me put this in economic terms. Imagine a civilization that built its entire economy around skyscraper living. Everyone lived at altitude. Ground level was just storage and infrastructure. All the wealth, all the culture, all the innovation happened in the towers. And then an earthquake hits and every tower collapses. 1,000 years later, archaeologists excavate the ruins. They find the foundations, the storage rooms, the infrastructure, and they conclude that this was a ground-level society. They miss the towers completely because towers don't survive earthquakes. That's what happened with Devonian canopy ecosystems. We're excavating the foundations and concluding that's all there was. But the towers were real. The biology proves it, the physics proves it, and the implications are staggering. Because if we missed an entire dimension of Devonian life, what else have we missed? How many other ecosystems existed in conditions we now think are impossible? How many evolutionary experiments happened in environments that no longer exist and left no fossils? The Devonian canopy is just the most obvious example, but it's not the only one. Consider deep ocean vents during the Cambrian. We have no fossils from those environments. Hydrothermal ecosystems don't fossilize well, but we know they existed. We know chemosynthetic life was thriving there. We just have no idea what it looked like or how diverse it was. Same problem, preservation bias. We only see what got buried in the right conditions. Or consider aerial ecosystems during the Carboniferous. We have fossils of flying insects with 3-foot wingspans, but we have almost nothing from the organisms they were eating. Because flying insects don't hunt on the ground, they hunt in the air, and aerial prey doesn't fossilize unless it falls into water immediately after a death. So we have the predators, but not the prey. Another gap. The Devonian canopy giants force us to confront an uncomfortable truth. Our understanding of evolutionary history is fundamentally incomplete. Not just missing details, missing entire categories of life. Because the fossil record isn't a faithful transcript of what lived. It's a heavily edited highlight reel biased towards specific environments and specific organisms. Everything we think we know about the progression of life, about the major transitions, about the diversity curves and extinction events, is based on that incomplete record. And when we find gaps, we tend to assume the gaps are real, that nothing lived there, that evolution skipped those niches. But what if evolution didn't skip anything? What if we're just blind to most of what happened? The giant trees prove we're blind. They prove that entire ecosystems that might have contained more species than the entire modern Amazon rainforest, can exist for tens of millions of years and leave almost no trace, just physics and inference. The fossils are gone, the organisms are gone, the atmospheric conditions are gone, but the logic remains. And the logic says something extraordinary was happening 40 miles up in the Devonian sky. What were those canopy organisms like? We can speculate. Lightweight arthropods with specialized respiratory systems, maybe book lungs modified for low pressure, maybe tracheal systems with active pumping mechanisms, exoskeletons reinforced with materials we don't see in modern arthropods because the evolutionary pressure to develop them no longer exists. Biomineralization techniques that produced ultra-strong, ultra-light structural proteins. Their sensory systems would have been alien. Compound eyes, adapted for the intense UV radiation at altitude. Maybe even UV vision, the ability to see wavelengths that modern organisms can't detect. Chemical sensors tuned to detect airborne pheromones across vast vertical distances. Vibration detection systems so sensitive they could feel the movement of prey on bark hundreds of feet away. Their reproductive strategies would have been equally bizarre. How do you mate when you're clinging to a vertical surface 40 miles up in thin air with temperatures below freezing? Maybe they released airborne pheromones that could drift for miles, attracting mates across vast distances. Maybe they had synchronized molting cycles timed to brief periods when atmospheric conditions were optimal. Maybe they didn't need to find mates at all. Parthenogenesis, asexual reproduction, just clone yourself and skip the complications. And their life cycles would have been shaped by the vertical gradient. Maybe larvae hatched at ground level and climbed upward as they grew, each molt allowing them to tolerate slightly higher altitudes until they reached their adult niche. Or maybe adults descended to lower altitudes to lay eggs, depositing them in bark crevices where temperature and pressure were more stable, then climbing back to the upper canopy to live out their adult phase. We'll never know the details, but we can infer the selection pressures, and those pressures would have produced organisms unlike anything alive today. Not just different species, different body plans, different biochemistries, different solutions to problems that modern life doesn't face. And then it all ended. The oxygen dropped, the trees fell, and an entire branch of evolutionary experimentation terminated. No descendants, no legacy, just extinction, complete and total. The canopy specialists had optimized so thoroughly for their niche that when the niche disappeared, they couldn't adapt. They were too specialized, too committed to their vertical world, and when that world collapsed, they went with it. This is the part that keeps me up at night. Not that they went extinct. Extinction is normal. 99% of species that ever lived are extinct. But this was different. This was the erasure of an entire evolutionary pathway. The Devonian canopy wasn't just a collection of species, it was a proof of concept. It proved that life could colonize altitude ranges we now think are impossible, that ecosystems could stratify vertically across 40 miles, that evolution could solve problems we didn't know had solutions, and then that proof disappeared. The atmospheric conditions changed, the giants fell, and the knowledge, the biological knowledge encoded in those organisms was lost. Forever. We can't get it back. We can't reverse engineer it from fossils because there are no fossils. We can't study their biochemistry because they're gone. All we have are questions and a haunting awareness that we're looking at the past through the narrowest possible keyhole. So what was living at the top of a 40-mile tall tree? We don't know. But it was there. It mattered. It represented evolutionary innovations we can barely imagine. And it's gone. Completely gone. Not even a genetic legacy. Because there are no descendants. The lineage is terminated. The adaptations died with them. And all we're left with is the physics that proves it must have happened and the fossil stumps that hint at impossible heights. This is revisionist history. Not because we're changing established facts, but because we're confronting established blindness. The standard narrative treats the Devonian as a ground-level story. Early forests, amphibians, fish evolving, all true, but incomplete. Because the most sophisticated ecosystems weren't on the ground, they were in the sky, and we miss them. For over a century of paleontology, we miss them. Not because paleontologists are incompetent, but because the evidence isn't there, can't be there. The preservation bias is too strong, and that means our picture of deep time is compromised, fundamentally compromised. We're not just missing details, we're missing dimensions. Entire axes of biodiversity that we can prove existed but can't document. And if that's true for the Devonian, it's probably true for other periods, other ecosystems, other environments where preservation bias blinds us. Which means every extinction curve, every diversity estimate, every model of evolutionary progression is built on incomplete data. Not slightly incomplete, catastrophically incomplete, because we're counting what fossilized and assuming that's everything that lived. But it's not. It's not even close. The giant trees are a warning, a reminder that the past is stranger than we think, that life has done things we can barely conceptualize, that evolution has run experiments in conditions that no longer exist, and that most of those experiments left no trace except the logic that proves they must have happened. So when you look at the fossil record and see gaps, don't assume the gaps are real. Assume you're blind. Assume that something was there, something extraordinary, and you just don't have the evidence to see it. Because if 40-mile tall trees can support ecosystems we'll never document, what else is missing? What other worlds existed in the spaces between the fossils? We don't know. And that's the point. We don't know, and maybe we never will. Because some chapters of life's story were written in ink that doesn't survive. They happened, they mattered, and they're gone. But here's the final twist, the economic angle that makes this revisionist history instead of just paleontology. Those trees weren't just biological oddities. They were carbon sequestration machines on a scale that dwarfs anything in the modern world. A single 40-mile tall tree, with its massive photosynthetic surface area and symbiotic canopy ecosystems, could have locked away more carbon in its lifetime than an entire modern forest. Multiply that by millions of trees covering the Devonian continents, and you're looking at a planetary carbon sink that fundamentally altered atmospheric chemistry. The oxygen spike that allowed these giants to exist, they created it by pulling carbon dioxide out of the air and splitting it into carbon for growth and oxygen as waste. They terraformed their own planet, built an atmosphere that supported their own growth. And when they fell, when the forest collapsed, all that sequestered carbon started breaking down and releasing back into the atmosphere. The Devonian canopy organisms didn't leave fossils, they left questions. And those questions don't have answers, only implications. And those implications are terrifying.